This lecture focuses on the factors that come into play when a substance dissolves. Particularly, we're going to focus on an ionic compound dissolving in water. Let's start by thinking about the process of dissolving. How does something dissolve on a molecular level? What is happening? What'll kind of help you visualize it is if you ask yourself why something, let's say table salt, dissolves in hot water easier, faster than it does in cold water. And that's because basically when something dissolves, just like when something chemically reacts, there are actually collisions taking place, in this case between the solute and the solvent, and then eventually the intermolecular forces will take over, and if the intermolecular forces are strong enough, the material will actually dissolve. So why do some things dissolve in water and other things don't? And you may have heard the expression like dissolves like. If not, it's a good thing to know. And what that means simply is that substances that are nonpolar, solutes that are nonpolar, will want to or will tend to dissolve in nonpolar solvents. And similarly, polar solutes will tend to dissolve in polar solvents. So like dissolves like. So when you're asked a question like that, the first thing you want to do is classify the substance as polar or nonpolar. So I'm going to say again, because it's going to keep showing up throughout the semester, that if you're fuzzy on how to determine if a molecule is polar or nonpolar, and that's when the shapes and the symmetry are important too, then you need to go back and review that. So hopefully you know that water is polar. Okay, it's not symmetric. It's got this bent shape. And so the things that'll dissolve in water need to be polar. So let's look at the ones over on the left. Diamond, that's just a bunch of carbon atoms bonded in a really beautiful way. I'm hoping that you know this is nonpolar, okay? In order to be a polar molecule, you have to have at least one polar bond, and then it cannot be symmetric. You don't, even if you have a polar bond, you don't want the polarity to cancel by having a perfectly symmetric molecule. Anyway, diamond is nonpolar because it's all the same atoms, so there are no polar bonds. So, of course, if you drop your diamond in water, thank goodness it's not going to dissolve. Sugar, on the other hand, we know sugar dissolves in water. We do it all the time. So could you explain on a molecular level why sugar dissolves in water? Well, first of all, sugar has polar bonds. It's got a bunch of carbon-oxygen bonds, okay? It's not perfectly symmetric. It looks like this on one end and just a hydrogen on the other, so it's not, doesn't make a mirror image of itself when it's folded over. And probably more important than that is these two substances can both hydrogen bond. And so the hydrogen bonding creates very strong intermolecular attractions between the two, and they will dissolve. Oil, take a look at that. And again, you probably know if you dump oil in water, they're not going to dissolve in each other, and that's because oil is nonpolar. So you're going to hear me say this a lot this semester, in case you haven't picked it up yet. Any compound that contains only carbon and hydrogen atoms, those are called hydrocarbons, is nonpolar. And that's because the electronegativity of carbon and hydrogen are very similar. Okay, so oil is nonpolar. That's why it doesn't dissolve in water. Sodium chloride is an ionic compound. All ionic compounds are extremely polar. So most ionic compounds will dissolve in water. Not all of them, most of them. And ethanol, we talked about this the other day. That's what's in alcoholic beverages. And again, kind of similar to sugar, it's going to dissolve in water because it is polar. And it's also capable of forming or creating hydrogen bonding with water, which is going to make it want to dissolve even more. So to better be able to explain on a molecular level why something dissolves, you should understand what it means to be polar. What does it mean when you say that something is polar? Okay, that means there's some degree of separation of charge in the molecule. So it doesn't have to mean it has ions, but it means that there's got to be different electron densities in different areas of the molecule. It might be very electron dense or electronegative in one area and not in the other. And how we show that is with these little squiggles. They look like I'm starting to make a figure eight, but then I don't close it. That means partial charge. Okay, so it turns out that electronegative atoms, those are the atoms that are located to the right of the periodic table, especially to the upper right. They are electronegative. They will have a partial negative charge. And elements that are located to the left of the periodic table or way down towards the bottom will have a partial positive charge. And so anytime you have this two atoms bonded to each other with different electronegativities, they're going to make a polar bond. Okay, so then the overall molecule is going to be polar unless it's completely symmetric. All right, so the bottom line is it depends on the strength of the intermolecular forces between the solute and the solvent. So let's test your understanding at this point. We have three compounds, and I know you don't know the names, so look at the structures. And which one of these do you think would be most soluble in water, and which do you think would be least soluble in water, and why? This is the type of question you would be asked on your exam too. I'm hoping that you would pick the ethanol as the most soluble because it can hydrogen bond with water. Now, ether would be the second most. Now, if ether were linear, it'd be completely symmetric and the dipoles would cancel, it'd be nonpolar, but it's not. So this is again when you need to remember how to draw Lewis structures. And if you drew the Lewis structure of that compound, it's kind of similar to water in that you have lone pairs of electrons on the central oxygen atom, forcing it into a bent shape, and therefore it's not symmetric. It is polar. And so that would be probably, well, it is soluble in water. And then the propane is completely nonpolar, not soluble because it's nonpolar, okay, as all hydrocarbons are. So continuing to talk about something dissolving on a molecular level, and just kind of verify what we talked about in the last slide, here are the actual solubilities of these three substances in water. Notice a couple of things. The units of solubility are usually grams per liter. I mean, it can be moles per liter. You have other units, but grams per liter is very common. And there will always be a temperature. So why is that? Well, it's because solubility depends greatly on temperature. So any measurement you take of solubility, that is how many grams of a solute will dissolve in a certain volume of solvent, you have to specify the temperature. All right, let's compare a few more molecules that are soluble in water. Just to remind you what miscible means. That means two liquids that are completely soluble in each other. So that means that the solubility of ethanol is so high in water that we just say it's completely miscible. You can just dump in as much as you want and they'll mix. But then what's happening to the solubility of each of these compounds? Okay, so let's go ahead and rank them. So ethanol is the most soluble. Down here is second most, 1,6-hexanediol. And third most is butanol. And fourth most is hexanol. So if you're feeling like you're starting to understand this, I would recommend turning the video off and giving it some thought. See if you can come up with anything. This one's tricky. And then I'll walk it through. Notice what's changing here. What's changing is the ratio of nonpolar parts of the molecule, right, to polar parts of the molecule. Okay, so we know the OH portion is polar, and we know the carbon-hydrogen portion is nonpolar. So each of these compounds has a polar section, and they each have a nonpolar section. But what's making, let's ignore the one on the bottom for a minute. Let's just look at these three. What's making the solubility go up in this direction? What it is again the ratio of the two. Ethanol, the OH represents maybe 1/3 of the entire molecule. I'm just winging it now. And then the OH in butanol represents maybe only 1/5 of the molecule. And in hexanol, the OH represents maybe 1/8, right? So the polar portion of these molecules is decreasing, which is making them less soluble. Now let's go on here. Why all of a sudden 1,6-hexanediol is it very, very soluble, extremely soluble? Not as much as ethanol, but even more than butanol. What's going on? Well, you have an OH on either end, okay? So that's 2 OHs, and that's going to help the solubility a great deal. Alrighty, back to the expression like dissolves like. You need to be able to interpret molecular diagrams as well as sketch them yourself if asked. So for any molecule to be soluble in water, or in anything really, it must be solvated. And what you may remember what solvation means, okay? Solvated means the solvent molecules surround the solute molecules, and by doing so, they do so because they're intermolecular attractions. So these dotted lines represent intermolecular forces, intermolecular attractions between the two. They're not real bonds. But obviously, the stronger the intermolecular force is, the closer the solvent molecules are going to want to pull to the solute molecule. Okay, so this is showing solvation here with a good diagram of it. You should also notice the orientation of the water molecules. Okay, the more electronegative element in each polar molecule has a partial negative charge. Okay, so the nitrogen would have a partial negative, the oxygens would have a partial negative, and all the hydrogens would have partial positives. We know the opposite charges attract, right? So this partial positive hydrogen is attracted to the partial negative oxygens. And so notice that the water molecules, the oxygens, are all oriented to be close to a hydrogen. So to talk a bit more about molecules that have a polar portion to them and a non-polar portion to them. Okay, so this whole non-polar portion is just carbon and hydrogen atoms. Okay, red in molecular models typically represent oxygen. And so the reason this is so important is because biologically speaking, and I don't know if you've gotten into this in your classes yet, but there are a ton of molecules in our body and in all biological species that have polar and nonpolar. Soap is another really common one, and that's the reason soap cleans dirt off in water. It has a polar end that allows it to be soluble in water. But it turns out that dirt, the grime we get on our body, is often nonpolar, like oils and things like that. And so we need a nonpolar portion. These all represent carbon and hydrogens. We need a nonpolar portion of soap that will dissolve or have intermolecular forces with oil and dirt so that it can remove it from your skin. Since most of this chapter will be focusing on dissolving ionic compounds in water, just kind of a reminder of what happens when an ionic compound dissolves in water. Always, this is 100% of the time, when an ionic compound does dissolve in water, it dissociates. Okay, always. So you should be able to draw that type of process. And when it dissociates, you've got to remember you have ions. They're charged species, and you've got to show that. And the AQ simply means it's dissolved in water. And that's really important that an ionic compound dissociates, because then in aqueous solution, the cation is quite a bit separated from the anion, and both of them individually are solvated by water. So looking at an image, a molecular scale image of solvation of an ionic compound in water, you can see right here we have the cation, and these are water molecules. So the cations, all the water molecules orient themselves so that the electronegative oxygen in water is most closely oriented to the positively charged cation. And the anion is the water molecules are going to be oriented such that the electropositive hydrogens are oriented close to the negatively charged anions. So again, be able to interpret these solvation diagrams as well as sketch one if you need to. So here's just kind of a close-up of solvation, just kind of show you, it may be easier to visualize here. So again, you have your anion, which it's going to be closest to the hydrogens of each water molecule. Okay, and then the cations are going to be most closely associated with the electronegative oxygen of water. Okay, so remember, these dotted lines are not real bonds, they're intermolecular forces. All right, here we go. This is a little bit more in depth of the theory of dissolving. There are 3 steps when you dissolve an ionic compound. The first step is you have to disrupt or overcome the intermolecular forces within the solvent itself. So if the solvent were water and you had a bunch of water molecules, right, they would be attracted to each other. They would have pretty strong intermolecular forces. Okay. And so the first step, if something's going to dissolve in water, these intermolecular forces have to be disrupted, loosened. And that's going to cost energy, okay? So the second step is you also, well, I guess they can occur simultaneously, I suppose, but you also have to disrupt the intermolecular forces among the solute molecules. They're going to have some type of attraction between each other, and that's going to cost energy, right? So there's going to be an energy cost to each of these. Okay, so why would it even happen if it costs so much energy? Well, because if something really does dissolve, all that energy gets returned, and more, hopefully, when new intermolecular forces between the solute and solvent are formed, okay? So then hopefully you get, that's kind of your money back on your investment. So hopefully you understood what I was trying to describe in the last slide. So let's just kind of do a quick check of your understanding. So here are the 3 steps that I said occur when you're trying to dissolve an ionic compound in water. And let's combine that with our knowledge about thermochemistry, thermodynamics. How would you classify each of these three steps as far as, is it exothermic, endothermic, no change in energy? So I suggest, because this is important to understand, go ahead and turn off the video, see if you can classify each of these, and then I will explain them to you. All right, so breaking or overcoming any type of intermolecular force or any type of chemical bond requires input of energy, which means that process is endothermic. Okay, so 1 and 2 are both endothermic because it requires energy to loosen up those pre-existing intermolecular forces. Now, the third one, when you make new intermolecular force, intermolecular attractions between the solute and the solvent as it dissolves, just as making any bond or making any intermolecular force, any type of electrostatic attraction is going to release energy. It's energetically favorable. And so that would be exo. Okay, so that's how you would classify each of the three steps in dissolving something. So let's think about why do, from a thermodynamic point of view, why do some things dissolve and other things don't? Okay, so keep in mind that when you are breaking up intermolecular forces, so pretend like this is sodium chloride. Remember, we have to disrupt the intermolecular forces that occur between the sodium and chloride ions, and that's going to cost us energy, right? It's going to cost energy. It's endothermic. And we'll go over these equations in a bit. On the other hand, and the same thing's going to happen to the solvent. Now, on the other hand, hopefully we get that energy we had to input. Hopefully it's given back out again if the intermolecular attractions between the ions and water are stronger, okay, than the pre-existing ones between the solvent and solute itself. You may have to listen to that a couple times, okay? This table may make it easier to understand. So let's look at dissolving salt, sodium chloride in water. Lattice energy is the energy of attraction between ions in an ionic compound. Okay, energy of attraction between ions in an ionic compound. Okay, so it's basically how strongly those ions are held together. Right, so the strength of attraction between a sodium cation and a chloride anion. Okay, that is lattice energy. So the lattice energy of sodium chloride, 779 kilojoules per mole. Hydration energy is referring to the energy released when ions are solvated by water. So basically, hydration energy is the new intermolecular forces that are formed between ions and water. All right. The hydration energy is 774. So again, okay, lattice energy is an endothermic. It's an energy cost. It costs us 779 kilojoules to loosen up the lattice energy in salt. But then we get 774 kilojoules of that back when sodium chloride and water are attracted to each other. So the net change in the enthalpy of solution for sodium chloride and water is +5, okay? It costs, the net energy cost, because it's positive, remember? So if it's positive, that's endothermic, it costs energy. So, but we know sodium chloride still dissolves in water. So this cost it does cost, but it's somewhat minimal. So let's look at potassium chloride. Potassium chloride has a weaker attraction, weaker lattice energy, but it also gets less energy or releases less energy when the ions of potassium chloride are hydrated. So the net enthalpy of solution for KCl, potassium chloride, is 16. It's not as likely to dissolve. I mean, it will dissolve, but not as likely. And lithium fluoride is going to be even less likely. Now remember that a negative delta H means exothermic, which is favorable, right? Okay. So sodium hydroxide is very, very soluble in water. As a matter of fact, you probably haven't experienced this, but if you dissolve sodium hydroxide in water, the solution gets very, very hot. You actually have to be careful. I'm going to kind of take a sidetrack here for a moment because this lattice energy ends up being important in the rest of the course, not quite as much in this unit, but later on. So these diagrams represent the lattice of ionic compounds. Ionic compounds, again, of course, are made up of a metal and a nonmetal, where electrons are completely transferred from the metal to the nonmetal. And so you end up with fully developed ions, which are strongly attracted to each other. Okay, so it's just ion-ion attraction. And so they make a three-dimensional array of ions, all really pounded together. Every single ionic compound is a solid crystalline substance because the ion-ion attraction is so strong. So let's compare a couple. Sodium fluoride, right, to magnesium oxide. Oops. Okay. Think a minute. You may have no idea, but see if you can speculate a little. Which one of these, based on their structure, do you think might be more or have a higher or lower lattice energy, strength of attraction of the individual ions? Well, it turns out that lattice energy, or the strength of attraction, and we're not going to plug in or do any calculations with this formula, but it's good to be aware of. So the lattice energy is dependent on the charge of each of the ions, and it's inversely dependent on the distance between the ions in the lattice itself. So let's think about what that means. The higher the charge on each of the ions, I can't spell, higher the charge, okay, the stronger the lattice energy, or stronger the attraction is. Okay? And the smaller the distance between the ions, okay, the smaller the distance between the ions, the stronger the lattice energy. So we want the distance between ions to be small. We want them really close to each other. And we want their charge to be really high. Well, that is if we want a big lattice energy. I guess that's not good for dissolving. But so lattice energy goes higher as charge goes up and as ions get closer together. So let's compare these again. Well, it's very clear that magnesium oxide has a much higher charge, okay? So each of the cation and the anion are both have an absolute value charge of 2, whereas sodium fluoride only has a +1 and -1 charge. And so magnesium oxide wins from the charge point of view. However, magnesium and oxygen are both farther down in the periodic table, meaning that they're larger, and that's not good for lattice energy. Okay, you've got a large denominator, it's going to make the lattice energy less. It turns out, though, that the charge on the ion is the number one important variable in determining lattice energy, and size is only important if the charges are all equal to one another. So it turns out that the lattice energy of magnesium oxide is much larger than that of sodium fluoride, about 4 times larger. So just to kind of verify that, see the lattice energy of magnesium oxide is almost 4,000. And for sodium fluoride, it's less than 1,000. What does that affect? Well, think about it, okay? The higher the lattice energy, so I'm just going to say Le. The higher the lattice energy, the more energy required to overcome that attraction, okay? More energy required to overcome that attraction. So what does that affect? Affects properties, melting point, boiling point, and solubility. So look how much energy it takes to melt magnesium oxide versus sodium fluoride. And then also, let me move this up. If you look at the solubility of each of them, magnesium oxide is much less soluble, much lower solubility than sodium fluoride because it takes so much energy to break up these intermolecular forces that you put magnesium oxide in water and it's like, no, 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 we don't like water enough. We're just going to stick around ourselves. So some kind of overriding tips you can use to predict solubility. And again, that becomes very important when we get into chemical reactions. So in general, no surprise, any ionic compound that has cations and anions with only a 1 charge is usually soluble, okay? Because the lattice energies are pretty small then, okay? So you have to remember, and this is from 1211 again, how do you identify metal ions that have a +1 charge when they're an ion? Well, group 1A, okay? So you need to remember what all the common ion charges are in the periodic table. Group 1A, they all have +1 when they're ions. Group 2A, +2. Transition metals you skip, then you go over to the group with aluminum. Group 3A, it's got +3. You get to the carbon group, 4A, can be plus or minus 4. They don't tend to make ions. And then when you get to the nitrogen group, it's -3. Oxygen group is -2. And the halogens with fluorine, chlorine, etc. is -1. So if you need to review that stuff, go ahead and do that. Similarly, ionic compounds with high charges tend to be insoluble, okay? So if the ions have a charge, if both of them have a charge of, let's say, +-2 or +-3, they're not going to be soluble. All right, so solubility table. This is going to be very important later. I just want to introduce the basic concept for you. So ions that have a ±1 charge, okay, tend to be soluble. Okay. But now, well, yeah, and here's ones with plus that are soluble too. But look at this middle group. It doesn't really follow the rules, right? I mean, what the heck? SO4 has a -2 charge, and it's usually soluble. It's kind of a high charge. Let's see. But carbonate has a -2 charge. Phosphate has a -3, and they're usually insoluble. Okay, I like that, right? I learned that big charges tend to make it insoluble. This is very confusing. Hydroxide only has a -1, and they are insoluble. All right, so the bottom line here is predicting solubility can get very complex. So it's not as simple as just the charge. It's the ability to be solvated by water, which also depends on how complex or bulky the ion is. So this is the solubility rules are something you'll have to have mostly committed to memory by the end of the semester. So at this point, I just wanted to introduce it. All right, so let's again tie in the thermodynamics we've learned about in this unit to solubility. We have talked about enthalpy of solution. Okay, that's the thermal energy required to either disrupt or make new intermolecular forces. But we know the entropy is just as important as enthalpy in determining whether or not something's going to happen. Now remember, free energy tells us if something is spontaneous. What does it mean to be spontaneous? It simply means it happens. Okay? So, if something dissolves, it happens, right? Something dissolves, it happens, and therefore we know that delta G has to be negative. Okay. So if you are observing something happening, that is a spontaneous process. Otherwise, you wouldn't see it happening. So let's talk about the entropy of solution a little bit. You may remember a couple of weeks ago when we were talking about change in entropy for a process, that dissolving an ionic compound in water has entropy change greater than 0. In other words, it's favorable. And I have mentioned to you to be able to predict the change in entropy that you think about freedom of motion. And so freedom of motion for an ionic compound dissolving in water is increasing, right? Because before it dissolves, it's a solid. Solid particles are very restricted in their movement. But once you dissolve ionic compound in water, it's going to dissociate into its individual ions, and that's going to give it a lot more freedom of motion. So the change in entropy for almost all, I can't even think of an exception, ionic compounds dissolving in water will be favorable, will be positive and favorable. Okay, so that's a good thing. So entropy almost always helps something dissolve. And this will let you know kind of from a mathematical point of view why higher temperatures also increase solubility, right? If entropy is always favorable, then increasing temperature is going to make it even more favorable, right? So, all right, just kind of a sideline. We're not going to go into detail here. It's just kind of introducing briefly the idea. The entropy of solution for an ionic compound in water is positive. It's increasing. It's favorable. Not true for a gas. You think about a gas like carbon dioxide. For making our carbonated beverages, we have to dissolve carbon dioxide, the gas, into an aqueous solution, whatever our beverage is. And in that case, the change in entropy is decreasing. There is less freedom of motion for those poor gas molecules when they're trapped in a beverage than they had on their own as a gas. Okay, so entropy is not favorable for dissolving a gas in water. And so because change in entropy is not favorable, you don't want a high temperature. And that's, okay, so this is kind of cool, I think. So if you take a Coke, right, and you open the top, and if you were in open top, you were to start heating it up, what would happen? You would eventually get rid of all the carbon dioxide, all the carbonation that's already dissolved in your Coke, right? And the higher your temperature, the faster you're going to lose all that gas, okay? And so that's because because entropy is unfavorable for gas and water. The higher the temperature, the more important you're making the whole unfavorable term, okay? So solubility, it's going to get less and less soluble at higher temperatures. So salts or ionic compounds get more and more soluble as the temperature goes up. Gases get less soluble as the temperature goes up. This is a solubility curve. And so on the y-axis is the solubility of the substance. On the x-axis is temperature. And so as we expect, as we increase temperature, the solubility of most ionic compounds goes up. They go up by, there's different sensitivities, but most of them go up. What the heck is going on here? This is showing that the solubility of this substance is going down as temperature increases. And that is because NH3 is ammonia gas. Okay? So that is typical of most gases. Their solubility is going to go down as temperature goes up. Let's do a kind of understanding check at this point. You may want to go back over the past couple of slides and make sure you kind of get the concepts, because I know it can get confusing. We've gone over a lot. And then see if you can answer this question. Why does the solubility of oxygen gas, or any gas, decrease with increased temperature? Okay. So that would be kind of a short answer theory question that you might be asked. So just to kind of get prime the pump here, for something to be soluble, for it to happen, for it to dissolve, as all spontaneous processes, we want delta G to be negative. And so using this equation, see if you can explain, we just went over it, why a gas would become less soluble. In other words, G becomes less negative as temperature goes up. The most basic thing I want you to understand with this question and related questions is that you can see by the equation that temperature only affects entropy. Okay? There's no temperature with the enthalpy term. So if a question asks you what the effect is on spontaneity or delta G with temperature, you need to focus in on the entropy term. Okay? So the correct answer is, we know that the change in entropy for a gas being dissolved in water, okay, is unfavorable. It means it has a negative sign, okay, unfavorable. So we know anytime entropy is unfavorable, decreasing, that we want to minimize temperature, okay? If we make temperature low, then this whole unfavorable term becomes less important. So then the correct answer over here is, as temperature increases, the unfavorable entropy term becomes more important. And therefore, as temperature increases, the solubility of a gas decreases. Just a couple more slides now. This slide might be able to help you visualize the answer to that question a little bit better. Again, for dissolving a gas in water, the change in entropy is negative, unfavorable. And so anytime one of these two terms, entropy and enthalpy, is unfavorable, you want to minimize it, okay? So in order to help make a gas soluble, you want temperature to go down, okay? In this case, they're saying, though, that temperature is increasing. So as temperature increases, this whole unfavorable term becomes more important. And so the substance is going to become less soluble, okay, because G will probably end up being positive. So let's kind of summarize the spontaneity or solubility of a substance. As all processes, the spontaneity, or whether or not it happens, depends on both enthalpy and entropy. And the entropy change for dissolving an ionic compound in water is almost always favorable. So delta S will have a positive sign. And when entropy is favorable, you want to maximize the favorableness. And so you want high temperatures to help something become more soluble. On the other hand, the entropy change for a gas in water is unfavorable, which means change in entropy will be negative. So that means this whole term, T delta S, is unfavorable. You want to minimize it. So you want a low temperature to help the solubility of gases in water. So before we completely get off the subject, thinking about dissolving a gas in an aqueous beverage again, looking at these images, can you think of another variable or factor that's going to affect the solubility of a gas in water? We know that temperature does. What other factor do you think might affect the solubility of a gas? It turns out that a really critical factor is the pressure. So that's why it's so important to keep a carbonated beverage sealed, because that increases the pressure inside the bottle. Actually, they're packaged with higher pressure. And because the pressure is higher, you can think about pushing all those carbon dioxide gas molecules. It's exhibiting force down on them so that they stay dissolved. And as soon as you take the top off, that means that pressure decreases. Okay, and when pressure decreases, the little carbon dioxide molecules are like, woohoo, we're free, nothing's pressuring us to stay. All right, so the last slide here. Now, this is a time when I'm probably going to sound like a broken record again, but anytime you're talking about the effect of pressure, it is really only going to be significant on the properties of gases. Liquids and solids are so tightly packed that they're pretty impervious to pressure changes. Okay, so really when you hear pressure, it's really only going to have an effect on gases. And just to kind of show you the magnitude, the x-axis in this graph is increasing pressure, and the y-axis is solubility. Check this out. Huge increase in solubility of all of these gases as pressure goes up. That is it for the little theories on solubility.